Good morning, myself Nancy from BSc First Year Chemistry Honors, making video on chapter number 3rd Stereochemistry of Organic Compound. Introduction. On the most important characteristic of organic compound is their ability to show isomerism. Isomers are the compounds which have the same molecular formula but different chemical and physical properties. It is of two types, structure isomer and stereoisomer. Structure isomer compound have the same molecular formula but different structure, different arrangement of atom within the molecule are called structure isomer and the phenomena is called structural isomerism. It is of six types. First, chain or nuclear isomerism. Compound having the same molecular formula but different arrangement of carbon chain within the molecule are called chain or nuclear isomerism. The phenomena is called chain or nuclear isomerism. For example, the formula of C4H10 represents two chain isomerism butane methyl propane as same as the likewise the molecular formula C6H14 represents the 5 chain isomerism. CH3 hexane and 2 methyl pentane 3 methyl pentane. The second is position isomerism, compound which have the same structure of the carbon chain but different only in position of the multiple double and triple bond or the functional group are called position isomerism and the phenomena is called position isomerism. Example butane 1-ene, but 2-ene. Likewise, but1-ine and but2-ine. The third isomerism is functional isomerism. Compound having the same molecular formula but different functional group are called functional isomerism and the formula is called functional isomerism. For example, the molecular formula of C2H6O represent the following two functional isomerism: ethanol and methoxymethane. Similarly, the molecular formula of C3H6O represent the four functional group propanone, propanol, propane 2 in 1-ol methyloxymethane. Further, the of functional isomerism example are carbolic acid and ether, aldehyde and ketone, diethane and alkene, alkane and alkyne, nitroalkane and alkyl nitrate, 1, 2, 3 amine, carbohyde and isocarbohyde. It, however, we noted here that orthoseriol, M-seriol, and P-seriol are themselves position isomerism. Fourth is metamerism, compound having the same molecular formula but different number of carbon atom or alkyl group on other side of the functional group are called metamers. The phenomena is called metamerism. Metamerism among the member of same homologous family. For example, ethoxyethane is metamer of 1-methoxypropane. The another example is diethyl thiother is metamer of methyl and propanyl thiother. It may be noted that the metamer may also be position isomerism. For example, pentane 2-on and trion may be regarded as position as well as metamer. Fifth is tautomerism. It arises due to 1,3 migration of hydrogen atom from one polyvalent atom to the other within the same molecule. Isomerism terms obtained which exist in dynamic equilibrium within the other are called tautomerism, and the phenomena is called tautomerism. There are several types of tautomerism, but keto-ethyl tautomerism is most important in this type of tautomerism. One form tautomer contains the keto group while the other contains the ethanolic group. The two simplest examples of ketol tautomerism are acetyl and acetone. The example are acetaldehyde and vinyl alcohol. Acetone converted to propane 1,2-ol. In simple aldehyde and ketone, the most in amount of ethanoic form is negligible, smaller. However, if the ethanoic form is stabilized by the intermolecular hydrogen bonding, such as in 1,3-dicarbonyl compound, the amount of ethanol form is much greater than the acetaldehyde or acetone. For example, in acetoacetic ether, the amount of ethanoic form is 7%. Similarly, the acetone also exists ketone in tautomerism, but the amount of ethanol formed here is much higher, 76%. Then, even in acetoacetic ether, this is due to the reason that keto group is much better electron withdrawing than the ether group. Essential condition for the aldehyde or ketone to exit the keto-ethanol tautomerism. It is essential that it must have at least one alpha hydrogen atom. Tux, acetone, phenone, butane, 2-on, and aldehyde all contain alpha hydrogen atom, hence show keto-ethanol tautomerism. Acetophenone, butane 2-in, and propane 1 aldehyde. In contrasting, benzaldehyde and benzophenone acid do not show keto-ethanol tautomerism. They do not contain alpha hydrogen atom. Similarly, the nitro compound also show tautomerism. Sixth is ring chain isomerism. Compounds have the same molecular formula but different opening chain and cyclic structure is called ring isomer, and the phenomena is called ring chain isomerism. Example represent C6H6 in form of propane and cyclopropane, which are the ring chain isomer. Similarly, butene or 2-methyl propane 1-in are chain isomerism of cyclobutane and methyl propane. Another double bond equivalent. Double bond equivalent is called index number or the hydrogen deficiency. The problem on structure isomerism and structure determination of organic molecule can be easily solved by the concept of double bond equivalent, which implies the sum of double bond and right present in the molecule. It give by the relation d dot b dot e is equal to sum of n bracket v minus 2 by 2 plus 1. where n is the number of different kind of atom present in the molecule and mu is represent the valency of the each atom. For example, D Be for MFC6H MF is equal to C3H6O, where 3 into 4 minus 2 bracket close plus 6 bracket open 1 minus 2 bracket close plus 1 into 2 minus 2 bracket close by divided by 2 plus 1 is equal to 0 plus 1 is equal to 1. This means that virus structure of C3H6O will contain either one double bond or one ring, as discussed below under example 3.2. Likewise, 2DBE implies either the two double bond or the triple bond, or two ring or one double bond or one triple bond or three double bond or one ring benzene ring or any other combination of ring, double bond and triple bond. Example 3.1. Write all the possible acyclic and acyclic structure isomer of hydrocarbon within the molecular mass 68. Solution. To determine the EBF, since the molecular weight of the hydrocarbon is 68, therefore the maximum number of carbon atom is equal to 68 divided by 12 is equal to 5, and the hydrogen atom is 8. Therefore, the molecular formula is C5H8. DBE for the C5H8 is equal to 5 into bracket open 4 minus 2 plus 8 bracket open 1 minus 2 divided by 2 plus 1 is equal to 2. DBE is equal to 2. Therefore, C5H8 may contain triple bond and two double bond and one double bond and one ring of two rings. First, acyclic isomer. Acyclic isomer contain a triple bond are pentane 1 ine 2 methyl butane 1 ine pentane 2 ene. B. Acyclic isomer contain two double bond pentane 1 3 diene 2 methyl but 1 3 diene and pentane 1 4 diene. Second, cyclic isomer. A. Isomer containing one double bond and one ring. For example, cyclopentane 1 methyl cyclobutane 3 methyl cyclobutane methyl ethyl cyclobutane 1 2 dimethyl cyclopropane 1 3 dimethyl 1 cycloprop 1 ene 1 ethoxy cyclopropane 3 ethoxy cycloprop 1 ene 1 ethyl cyclopropene. Example, thus these are all 14 cyclostructure isomer with the molecular mass 68 or molecular formula C5H8. Acyclic isomer are acetone, propanol, prop-2,1-ol methoxyethane. Cyclic isomers are octane, 2-methyl-oxirane, cyclopropanol. Thus, C3O H6O have 7 isomers. Note, while writing the structure isomer for any given molecular formula, tautomerism is neglected unless otherwise asked for. For example, tautomerism for acetone and that propanol have not been induced while containing the total number of structure isomers. Stereoisomer. Isomer which have the same structure formula but different relative arrangement of atom or group in space are called stereoisomer. And the phenomena is called stereoisomerism. Stereoisomer are of two types: conformation isomers. Stereoisomer which is different in relative position of atom within the molecule which can be interconverted simply by rotating about the sigma bond are called conformational isomer. In another word, interconverging of these isomer does not require breaking and remarking of covalent bond. Configurational isomerism, stereoisomerism, which can be interconverted by breaking and making of covalent bond and not simply by rotating about the sigma bond, are called conformational isomerism. These are of two types: optical isomerism and stereoisomerism. Optical isomerism. Certain compound can exist in stereoisoform which cannot be superimposed on one another. In spite of this difference in the relative specular arrangement of atoms, these isomers have identically physical properties such as melting point, boiling point, refractive index, density, solubility. They also resemble another in most of their chemical reaction. However, they different only in behavior toward plane polarized light. One rotate a plane of polarized light toward right but another toward left but to the same extent. Such a pair of compound are called optical isomerism and the phenomena is called optical activity. Some general concept about the optical isomer. In order to understand the phenomena of optical isomerism, we must be familiar with the following term. Plane polarized light. Ordinary light consists of electromagnetic wave or different wavelength. Monochromatic light, on the other hand, consists of only one wavelength. It can be obtained either by passing the ordinary white light through a prism or recording or by using the source which give light of one wavelength. For example, the sodium lamp limited yellow light of about 589.3 nanometer wavelength. Whether it is ordinary light or monochronic, it consists of waves having the migration in all the plane perpendicular to the line of propagation of light. If such a beam of light is passed through a nickel prism made of from a particular crystalline form of CaCO3 known as cacellite, and the light that come out of the prism have vibration only in one plane. Such a beam of light which have vibration only in one plane is called plane polarized light. An ecloprism used to obtain polarized light is called polarizer. Second, angle of rotation. The angle in degree through which the plane of the polarized light get rotated on passing through the solution of a optical active compound is called angle of rotation. It donated by a Greek letter alpha. Polarimeter is the instrument used by measuring the angle of rotation of plane polarized light is called polarimeter. It consists of light source, usually the sodium lamp, two nickel prism and a polometer tube. The nickel prism near the light source is called polarizer, while that near the eye of observer is called the analyzer. The axis of polarization of polarizer is fixed while that of the analyzer can be changed. In between the polarizer and the analyzer is placed a glass tube called polarimeter tube which contain the solution of the optical substance. The solid line represents the plane of polarized light before the broken line represents after passing through the solution of the optical active substance. If the axis of the polarization of two nickel prism is held parallel to each other and the polarized tube is empty, the plane polarized light from the polarizer pass through the analyzer without any change in intensity. Conversely, if the two nickel prisms are held with their axis of polarization perpendicular to each other, no light pass at all. However, when the solution of any optical active compound is placed between the polarizer and the analyzer with their axis of polarization parallel to each other and the intensity of the light come out of the analyzer is lesser than that falling on the polarizer. In such cases, in order to have maximum transmission of the light, the analyzer has to be rotated through some angle in direction of the other. This angle through which the analyzer has to be rotated to get the maximum transmission of light is called the angle of rotation, and the angle of rotation alpha of any optical compound depend upon the flowing factor, nature of optical active substance, concentration of the solution in G by ml, length of the solution through which the light is passing, nature of the solvent, wavelength of the monochronic light used, temperature of the sample. Fourth, spatial rotation. In order to compare the rotatory power of different optical active substances, the activity is usually expressed in terms of spatial rotation. The spatial rotation of optical active substance is defined as the degree of rotation observed when the plane of polarized light is passed through a tube having a path length 1 decameter and the concentration of 1 gml of the compound at the specific temperature and wavelength is denoted by the alpha, where T temperature, D is the wavelength and of the light used. Usually D of the sodium having a wavelength of 589.3 nanometer is used as a source of the chromic light. Since it is not always possible to dissolve 1 gram of optical active substance in 1 ml of solvent, therefore the measurement of the angle of rotation is usually carried out at same lower concentration and the specific rotation in them calculated by the application following equation. Observed of the rotation by L into C is equal to alpha bracket D by T by D, where L is the length of pedometer tube in decameter and C is concentration of dose substance in gml. While reporting the specific rotation of optical active substance, it is compulsory to be included that the concentration of solution used by measurement along with the solvent in parentheses after the specific rotation. For example, the specific rotation of cane sugar at 293 K using the D-lining sodium vapor lamp is plus 66.5 degree. Plus sign before the angle of denation that of sugar cane is rotatory. Just like the melting point, boiling point, the density and refractive index, etc., the specific rotation is the characteristic of the property of optical active compound. Optical active discovery. The phenomenon of optical active was described by the French chemist Louis Pasteur in 1848. He observed that when the concentration solution of sodium ammonium tetrate was allowed to crystalline, the type of crystal separate out working carefully can magnify glass, and a pair of twister Pasteur was able to separate the crystal into two pieces, one of the right handle and the other of the left handed crystal. Each type of the crystal, when dissolved in water, found to rotate the plane of polarity right. One sodium rotates the plane of polarity light toward the right while the other toward the left, but the same extent. Later on, millions of the molecule has been discovered which rotate the plane of polarity light. Such substances which can rotate the plane of polarity light are called optical active substance, and the property of the substance to rotate the plane of polarity light is called optical activity. A substance which rotates the plane of polarity light toward in clockwise direction is called dextrorotatory and usually used by a prefix d or plus sign. On the other hand, the which rotate the plane of lateral light toward the left, it is anti-clockwise direction is called leo-rotatory and is usually represented by prefix L or negative sign. 3.43 Celerity. An inspection of the molecular structure of optical active compound indicate that all these compounds have chiral molecule. A molecule is said to be chiral or dissymmetrical if it is not superimposable on the mirror image, and the property of superimposability is called celerity. On the other hand, a molecule or an object which is superimposable on its mirror image is called a chiral, मतलब कि non dissymmetrical or symmetrical. To understand the term chiral or acrylar, let us consider the alphabet P and A, whereas P is crilar and A is acrylar as shown in figure. Simply, the alphabetic F and J are crilar, where M and O are acrylar. The common example of the crilar object is the human hand. You hold your left hand before a mirror. The image look that of the right hand. If you do not have a mirror available, hold your hand toward with the another, the palm facing each other. You see that the mirror image. Try the superimposable your hand both palm down. You cannot do it. Human hand is a crueler, simply rolls shoes or are clear object you have ever. Why can't you wear the left hand gloves in right hand? This is because non superimposable images of each other. A button, a spherical is cube, and the most shock on the other hand are acrylic. Simply, they are superimposable on their respective mirror image. Molecular clarity and asymmetric carbon. Let us now extend the concept of chirality to the organic molecule. The chirality in organic molecule exists due to tetrahedral nature of carbon. The four valency of carbon is directed toward the four corner of regular tetracodone as proposed by J. von Hoff and the C. Lee Bell independently. To isolate this, let us consider the molecule of 2-chlorobutane. One in this molecule C2 carbon is attached to four different substitution HCl, CH3 and CH3CH2. Such a carbon atom which attach to four different substitution is called asymmetrical carbon atom or a acrylar carbon atom or simply acrylar center. A simple acrylar carbon atom indicated by asterisk. Further, it is represented noted that it is the carbon which make a molecular dissimilar or natural as explained below. The mirror image of A is A1. To check the superimposability of A1 over A, rotate the molecular toward 180. It in such a way that C and Cl bond in new structure A2 object in same direction as that in structure A. Now superimposable of A2 over A, we find that A and A2 are not superimposable no matter how the turn and twist molecule without breaking the bond. We may get a central carbon atom too of the superimposable. For example, H and Cl can be superimposable, but the spectral orientation of CH3 and CH3 and CH2 group are different in A and A2. In structure of A, CH3 CH2 is pointed toward the, while in A2 it is pointed toward for you. Thus, a and A2 are non-superimposable mirror images and hence 2-chlorobutane is a clearer molecule. However, if the two substance atom or a group attached to the carbon atom are similar, the similarity or dissimilarity is most lost and the molecular become symmetrical or acorrelate. Since a simple rotation through 180 about its axis will make it superimposable on its mirror image. For example, consider the molecule of 2-cyclopropene B and the mirror image B1 to check the superimposability of B1 and over a B, rotate the molecule to 180 to get B2. Now try to superimpose the structure of B2 over B. You will find that B and B2 are superimposable since 2-chloropropane R is an acyclic molecule. For the above discussion, it is followed that celerity probably exists due to presence of asymmetricity or chiral carbon atom. As we shall discuss later in this unit, that the statement, however, is not now true. Nowadays, the presence of chiral or the asymmetrical carbon atom in a molecule always make it chiral and hence the optical active. Example, lactic acid, glyceric acid, or the dioxypropanol bromochloroiodomethane all are chiral dissymmetrical molecule and hence are optically active. Element of symmetry. The superimposability of an object and its mirror image can be tested with in the help of three elements of symmetrical such as plane of symmetry or a center of symmetry or an alternative axis of symmetry have at least one or more element of symmetry. Plane of symmetry or mirror plane or alpha plane. The most common observed element of symmetry is plane of symmetry or mirror plane or alpha plane. It is defined as imaginary plane which divide the molecule into two equal halves have that one half of the molecule is mirror image of the another. It may throw atom between atom or both. Thus, a spherical sphere is a aspherical or it is a plane of symmetry. On the other hand, human hand, left or right, is clearer since it has no element of symmetry. In a vertical plane, has shown, but It is not a plane of symmetry since it divided the right hand into two unequal halves. Like the object, some molecule can be possess plane of symmetry. For example, 2-chloropropene have a plane of symmetry which is perpendicular to the plane of paper and pass through ClNCH atom. Similarly, the mesotric acid has a plane of symmetry which is perpendicular to the plane of paper. Superimposibility of the representative mirror image and hints are optically inactive. On the other hand, the molecule cannot be superimposed on the respective mirror image and hence an optical active. Second, center of symmetry. A center of symmetry is defined as point from which line when drawn on one side and produce an equal distance on the another side will meet identical point. It is also called center of inversion and is usually denoted by the symbol C1. For example, both transition of 1,3-dicyclobutane and mesotrachic acid has a center of symmetry, hence are called optically inactive. Third, alternation of the axis of symmetry. A molecule is said to be possess an unfold alternative axis of symmetry in the rotation through an angle of C660 and about this axis then by reflecting a plane perpendicular to the axis give a molecule which is indirectionable from the original molecule. Consider this the molecule shown in figure 3.11. Hence, Z plus and Z negative represent the acrylic group as C plus C CH3 CH2 H5 and the negative CH CH3 C2H5 represent rotation of A through the 90 through the axis AB which represent through the center of the ring and the perpendicular to it plane give the molecular B. The reflection of B give the original molecule stocks. This has a fourfold C60 divided by 90 is equal to 4 alternative symmetry and hence is chiral. Since a one-fold alternative axis corresponding to a plane of symmetry and toward the alternative axis corresponding to the center of symmetry through absence of an alternative symmetry is a necessary and the substitution condition for a molecule to be optic activity. Relationship between asymmetrical, disymmetrical, and heterogeneity. It is interesting to note that while describing optical activity of organic compound, two term asymmetrical and disymmetry has been used without any distraction that there exists is stable difference between them. A molecule which have no element of symmetry, alternative or simple of symmetry is called asymmetrical molecule. Such a molecule is usually optical active. On the other hand, a molecule which have no alternating axis of symmetry, which may or may not be simple of symmetry, is called disymmetrical molecule. Like asymmetrical and disymmetrical molecule are also usually optically active. Considered for example, 2-butanol, it has no element of symmetry. It is an asymmetrical molecule, hence it optically active. Now, the projection formula of optical active tartaric acid, it has simple axis of symmetry in the center of the molecule. It is shown by dot and process perpendicularly to the plane of the paper. Rotation through 180 degree about the axis give formula which considered with the original formula. Tux optical active tartaric acid has simple C2 axis of symmetry and hence it is not an asymmetrical but it is disymmetrical molecule. Near there is near nevertheless it optical activity tux all the asymmetrical molecule are disymmetrical but all the disymmetrical molecule are not symmetrical although both of them are optical active. To avoid this confusion, another term called celerity has been introduced and it more widely used these days. It is simply related optically active with the non-superimposable mirror image relationship and not to the absence of element of symmetry. Thus, a molecule is said to be trill or hence called active if in its mirror image is not superimposable. Let's draw the mirror image of third of the first. Since the structure third is not superimposable on the structure first, therefore tartaric acid is chiral and it optically active even though it containing a C2 axis of symmetry. Thus we consider that while plane and the center of symmetry produce celerity, the compound which have only simple axis of symmetry can be chiral and hence optically active. Sterogenic center of Strio center. We have started there above that tetrahedral carbon atom attached to four different atom or group are called asymmetrical and trill carbon atom. However, in 1984, K. Mislow and J. Zali pointed out that the use of the term chiral carbon has created conceptual confusion. According to these scientists, it is not the atom which is chiral, but actually it is the molecule which is chiral. In the another word, chirality is geometrical property which prevails and affect all the part of the chiral molecules. For example, all the atom of 2-butane are in a chiral environment and hence all are said to be chiralitic. However, we have not used the term chiral carbon and such as C2 butanol in the same sense. We have simply used this term to indicate that if any two atom or group attached to a carbon are mutually exchange, a new stereo is obtained. In other words, C2 of 2-butanol should be designed as a center of stereoisomer and stereogenic center, not a child center. Further, consider the cis and trans stereoisomer of 1,3-diochlorobutane. Hence, carbon atom 1 and 3 are centered of this stereoisomer but not child center since each carry two identical groups. Therefore, these are perfectly called a center of this stereoisomerism or carry two identical groups. Thus, the stereogenic center may or may not be child, the charity center of charity. For example, the stereo center C2 in the butanol is child but C1 and C3 is cis and trans. 1,3 diochlorocyclobutane is a child. Thus, all the child centers are stereogenic, but all the stereogenic centers are not child center. Therefore, in this unit, hence after we shall use the term stereocenter or stereogenic center instead of child center. Configuration and Fischer projection. The stereo has the same molecular structure but different relative arrangement of two atom or group in a space. Its spatially arrangement of atom or group which characterize or define a particular stereomer is called the configuration. The configuration of organic molecule can be visualized by infection impacting of their model and three-dimensional structure depending upon hence how old the molecule and the 3D structure of the organic compound may be represented a number of ways, but the mostly common used 3D model is flying bag model. In this model, three types of line are used. A solid, thick solid line represents the bond line above the plane of the paper projection toward the observer. Ordinary solid line represents the bond line within the plane of paper, while the dotted line represents a line below the plane of paper projection away from the observer. In this method, sometimes the dotted wedge is replaced by the dotted line for purpose of simplicity. However, it is not always convenient to construct this model or draw the three-dimensional structure. It therefore becomes necessary to devise some method to represent the three-dimensional structure on two-dimensional surface, such as a paper of blackboard. In 1891, the German chemist Elvis Fischer introduced a simple method to represent the special arrangement of atom group around the Schur center on a paper. This planar representation is called Fischer projection. The main point of this produce are as given below. First, molecule of any chiral compound containing the chiral center is viewed in such a way that two of the group attached to register are horizontal and pointed toward the observer, while the other two are vertical and pointed away from the observer. Second, various atom or group attached to the chiral center are then projected on the plane of paper in the form of cross. By converging, the chiral center is not shown, but it believed to lie at the intersecting of horizontal and vertical bone. Third, if the chiral molecule containing two or more child center, each child center must be viewed individually in a manner described above. As far as possible, the vertical part of the projection formula text obtained should represent the longest chain of the carbon atom with the most oxide carbon COOH in lactic acid, CHO in the silyl aldehyde and CH2OH into methyl 1 butanol. At the top, this carbon atom in then number according to the IUPAC nomenclature. To to drive the three-dimensional structure of a molecule from the Fischer projection, we simply revert the process described above. For example, depending upon which bond are drawn in the horizontal, which bond are drawn in vertical position, Salver-Fisher projection can be written for the same compound. It is therefore necessary to compare two different projections to see where they represent the same different compound. To test the identification different Fisher projection for the compound the follow represent must be observed. A Fisher projection first. A Fisher projection must not be lifted from the plane of paper and turned over. Such operation give the anisomer of original molecule. For the structure first and second represent the anisomer of bromochlorofluoromethane. Second, the Fischer projection may be turned through 180 in the plane of paper. Such a observation gives the same stereo. For example, the stereo of third and fourth represent the stereo of lactic acid. Third, a Fischer projection should be turned over the 90 and 270 in the plane of paper. Such an operation gives the anisomer the original molecule. For example, the structure 5th and 6th represent the anisomer of 2-methyl 1-butanol. Fourth, on the intersection of the group attached to the chiral carbon, an even 2 or 4 number of the time in a Fischer projection without affecting the configuration of molecule. It may be noted that the number of interchange should be even no matter which group are exchanged at useful cooperatory of the rule is that we can hold any one group state and rotate the other three in either clockwise or in anti-clockwise direction. For example, if the COOH group in the Fisher projection seventh for the align is fixed and the other three group rotate in the clockwise direction. The projection of 8th and ninth tucks obtained are identical and represented the same to align. Optical isomers. Although optical isomer compound exists in two or more isomers from which difference from one another in the relative spatial arrangement of atom or group. These two isomers which resemble one another in their chemical reaction, most of the physical property but different only in their behavior toward the plane polarity light are called optical isomer and the phenomena is called optical isomerism. Optical isomerism in the compound containing one Crayler center and or one stereogenic center enantiomer. This is the simplest kind of optical isomerism and was discovered by the Fisher chemist Louis Pasteur in 1848. As stated above, an optical active compound can be exist in two or more stereomeric form called optical isomerism. Optical isomerism, which are non-superimposable mirror images of the each other, are called the anisomer, and the phenomena is called anisomerism. The anisomerism has been identical and physical chemical property but rotated the plane of polarity light in opposite direction but to the same extent. To understand the phenomena of an isomer, let's us again consider the molecule of bromochlorofluoromethane. It exists in two steo form, first and second, which are known superimposable mirror images of each other. Further, each of the two isomer is optical active and rotated the plane of polarity light in the opposite direction but to the same extent. First and second represent the enantiomer of bromochlorofluoromethane. The enantiomer which rotate the plane of polarity light toward the right is called dextrorotatory and is represented D positive, while the enantiomer which rotate the plane of polarity light toward the left is called leolotatory and is represented by L or negative. However, it may be emphasized here that it is not possible to tell us as which isomer is positive and negative just by looking at the structure. It can be defined experimentally. Similarly, the lactic acid and butane-2-ol both show the enantiomer since the molecule cannot be superimposable on the mirror image. Condition for an enantiomer. It may be noted that the necessary and sufficient condition for molecule to exist in enantiomers and hence optical active is chill or the dissimilarity of the molecule and its mirror image must be non-superimposable. It may or may not be containing chiral or asymmetrical carbon atom. Usually, the presence of one or more chiral carbon atom causes the molecule to show an enantiomer and hence optical activity, but certainly it is not the necessary and sufficient condition. For example, tartaric acid containing two chiral carbon atom but does not show an enantiomer and is actually optically inactive. This is due to the reason that it contains a plane symmetry which divided the molecule into two equal halves so that one half of the molecule is a mirror image of the another. As a result, mesotartaric acid and its mirror image are superimposable. In another word, mesotartaric acid is an H or non-disymmetrical or symmetrical molecule. Hence, it is not show an isomer or optical activity. Thus, the optical inactive of mesotartaric acid is used to internal composition. The rotation caused by one half of the molecule is exactly cancelled by an unequal opposite rotation caused by the half of the molecule. On the other hand, there are many compounds which do not contain the child and carbon atom but their molecule are circular or asymmetrical. Hence show the enantiomer or optical activity. For example, alkane or O distribution diphenyl do not contain the child carbon atom but their molecule are superimposable on the respective mirror image and hence show enantiomer or optical activity. Property of an enantiomer. The important property of an enantiomer are they have identical physical properties such as melting point, boiling point, density, solubility, refractive index, and they differ only in the direction of rotation of the plane polarity light. One rotates the plane of polarity light toward the right and another rotates toward the left but to the same extent. Second, enantiomer with identical chemical property except toward the optical active reagent. The chemical reaction of the enantiomer of any optical active compound with the optical inactive reagent such as HBr, H2SO4, CH3COOH are not only the same but also at the same rate. For example, it is the two enantiomer of butanol not only give the same alkane but two butanol on the treatment with the concentrated H2SO4 but the rate of these reactions are also identical. On the other hand, the reaction of an enantiomer with optical active reagent proposed at different rate. For example, if we separate the acidify the enantiomer of 2-butanol with lactic acid, the rate are found to be different. Enantiomers have different biological property. In biological system, all the reaction are catalyzed by the enzyme which themselves are optically active compound. These reaction of an enantiomer with enzyme are so stereospecific that the quite often the reaction with one of the enantiomer does not take place at all. For example, we eat the D positive glucose in the form of carbohydrate daily. This is metabolic by the in the body to produce CO2, H2O, and a lot of energy is generated. That's the energy used for our day-to-day work. However, if we eat the glucose, it does not metabolize and is excreted in such through the urine. Simply, the quine being down the malaria fever but do not note the quine negative. This difference is related to enantiomer is great importance in biochemistry and chemistry taken place in our body. Chill or acyclic molecule with the two stereocenter or optical isomer in a compound containing two stereogenic centers. So far we have been discussed that the presence of stereocenter or chill or asymmetrical carbon make the molecule dissymmetrical or as a result the compound containing one stereocenter can exist into two stew known as an enantiomer. Therefore, it is accepted that the compound which contain two or more stereogenic center which exist in more than two stew form to exist. This let us now discuss the optical active isomerism of the compound containing two stereoisomer center. These are the stereocenter can be either dissimilar when the atom or group attached to the child carbon are different from the present on another. Similarly, when the atom or group attached to the two or are same, the two representative example of such compound are 2-dichloropentane and tetraeric acid. Let us now discuss about the optical isomer in one of them separately. Compound with two dissimilar stereogenic center called D-estomers. The compounds such as 2,3-dichloropentane contain two dissimilar stereogenic center and hence can exist into four isomerism form first, second, third, fourth. As for all are optically active. Stereoisomer first and second are non-superimposable mirror image of such other hints represent a pair of isomer. One of these isomer is stereo. This isomer, which while the other is leolotatory. Likewise, the stereoisomer third and fourth are non-superimposable image of each other and hence represent the another pair of an isomer. One these the rotatory and the another other is leo-rotatory. This compound containing two dissimilar stereogenic exist in the four optical isomer which can be regarded as a two pair of an isomer. Now the question arises as to what is the relationship between any two pair first third fourth second third second fourth as inspection of these structure reveal that none of these pair are mirror image of each other and nor can be the interconnected by the rotation about carbon and bond. Such stereoisomer which are not mirror image of each other are called distereo or simple stereoisomer. Thus first fourth, second third, second fourth or represent a pair of this stereomer. In another word, this stereoisomerism are the stereoisomerism which are not an isomer. They have the same configuration at the stereocenter or the chiral carbon but different at the other. The property of this stereoisomerism. Since this stereoisomerism are the stereoisomerism which are not mirror image of each other. These properties are different from those of the enantiomer which are mirror image of each other. Some important property of this isomerism. First, physical property melting boiling point. Unlike the enantiomer, these enantiomers have the different physical properties such as melting point, boiling point, solubility in a solvent, density, refractive index. Separation. Due to difference in physical property, this enantiomer, unlikely an enantiomer, can be separated by the physical method of separation such as fraction distillation, fractional crystallization, chromatography. Behavior toward a plane polarity line. This enantiomer may be either optical active or inactive. For example, the stereoisomer which are also regarded as this stereoisomer are optically inactive, which I while other are usually optically active. Even the optical active stereo may be same or opposite sign of rotation. Chemical property unlikely the enantiomer they say have the similar but not identical chemical properties since the rate of reaction of this isomer with the chiral and natural reaction are generally different. This is due to the reason that either the and resin nor the transition state are the mirror image of each other. As a result, this stereoisomer have different energy of activation for a particular reaction and hence react at the different rates. Optical active isomerism. Relationship between enantiomer and meso compound. Let us again consider the three stereoisomer of tartaric acid. An inspection of the structure of positive tartaric acid and negative tartaric acid and meso tartaric acid reveal that these are not mirror images of each other nor can be. They are interconverted by the form rotation about the carbon-carbon bond. Thus, the positive tartaric acid and mesotartaric acid are these isomers, so the negative tartaric acid and mesotartaric acid begin this isomer. The property of mesotartaric acid are different from those of positive and negative tartaric acid as shown below. Thorough and distoisomers. Molecule of the type are carb and are containing the two stereogenic center have the has been exclusively used is mechanically sturdy and a special nomenclature has been developed for such system. This nomenclature is based upon the naming of two four carbon atoms sugar, ethylose and thyrose. If the two group A in the projection formula are on the same side as the in the etheric, the isomerism is called heteroisomerism, and if they are on the opposite side as the hydrochloric group in the stereo, the isomerism are called stereo isomerism, as in stated the diastereomerism 3 bromo 2 butanol. At the first sight, it might be appear that the Fisher projection formula as shown above should be abbreviated represent the dis-stereoisomerism of the compound containing the two charged carbon atom. However, a closer look at the model from which this projection formula has been derived reveal that the model and therefore the projection represent the molecule in the less stable explic form. The crowding between the substitution on the C2 and the C3 are at maximum, but the real shape of the molecule is not like this, but more closely corresponding to the arrangement of C2, C3 are rotated by the angle of 180 degree, so that their substitution are as far apart as disable to be despite the molecule in it actually secrete form rather than it hypothetically explicit form as the shown in the Fisher projection. The two best way of to represent such molecule in a more stable secret form are show horse representation and Newman projection formula. The Fisher formula can be easily transformed in the Schauhaus representation by the first making the explicit form and then rotating through an angle of 180 around the C2 and C3 bond as shown in figure 3.20. Similarly, the phasor projection formula of hetero and stereo 3 bromobutanol can be transferred to the Newman projection formula by first making the explicit form and rotating through an angle of 180 degree. C2 and C3 bond as shown in figure C.21. A compound of the above three represent may be helpful. The Fisher formula clearly show at the glance whether one is dealing with the hetero and or stereo form, but the Schauer and Newman formula do not usually require a mental process of rotation above C2 C3 until one can be decided which further the Schoenhofer formula are quite convented to represent the excel as well as staggered form from the Newman projection formula for the escape form look awkward. Let another method of representing the compound containing two stereogenic center is by mean of flying back formula as shown in figure 3.22. The hetero and the thero 3 bromo 2 butanol optical isomer in a compound containing two more than two stereogenic center or child carbon atom. From the above discussion, it can follow that the number of stereomeric depend upon the number of the stereogenic center or carbon atom present in the molecule. For the compound containing one stereogenic center, therefore are two stereoisomer. For the compound containing two this similar stereocenter, the number of stereoisomer is 4. The working on the similar line, we consider that the compound containing this similar stereogenic center exhibit 2 and stereoisomer. To insulate this, let us consider a 6 carbon atom sugar. It has been have for this similar stereogenic center and hence exhibit 2 4 is equal to 16 stereoisomer. All these isomers are known as and corresponding to D and L form of alsos, alterose, glucose, mannose, glucase, endose, lactose, and talose. In the another word, glucose is one of these 16 isomers. If, however, one or more acyl atoms become identical, the number of stereoisomers is always less than the predicated on the basis of 2n rule. Calculation the number of stereoisomers. The total number of stereoisomers depend upon the nature of molecule and the number of stereocenter it contains. Uh, Following cases arises when the molecule is unsymmetrical containing the stereogenic center or 12 carbon atom. The number of critical isomer 0, D positive, L negative is equal to 2 and the number of mesoform is 0. The total number of stereoisomer optical meso is equal to 2n. For example, CH3 CHBr CH3Br COOH 2-bromobutanoic acid is unsymmetrical, has two dissimilar shell carbon. Therefore, the number of optical isomer is equal to 2n, where n is equal to 2. So 2 के power 2 is equal to 4. The number of mesoform is 0 and the total isomerism is 4. Second, when the molecule is symmetrical and has even number of stereogenic center or shell carbon atom, the number of the stereoisomer is calculated as follows. The number of optical isomer is equal to की power n minus 1 and the number of meso is 2 की power n 2 n by 2 minus 1. Total number of stereo is equal to 2n की power minus 1 plus 2 n by 2 minus 1. For the example of tartaric acid has total number of 3 stereoisomers as calculated below. When the molecule is symmetrical and hence odd number of stereocenter, the number of stereocenter is calculated as follow. For example, the tartaric glutaric acid has 3 stereoisomer center has the molecular formula is dissymmetrical. Therefore, the total isomerism is 4. 4 stereoisomerism are. It may be noted that C3 in the pair of an isomer first and third is no stereogenic center since two chiral groups are identical. This is because the interchanging of H and OH at the C3 is either an isomer lead to be identical structure. This is best seen by turning the new structure by 180 degree in the plane of paper. However, in each mesoform, the member of this set interchange H or OH at the C3 converted one form to another. Therefore, C3 is a stereogenic center but not a chiral center. Such a center has also been called as pseudo chiral center or pseudo-asymmetrical center. Prochilarity and prochiral molecule. A carbon atom in a molecule is called prochiral if the representation of one of its hydrogen atom by substituting atom or a group produce a chiral center. For example, C2 is a proponic acid is prochiral since the replacement of one H at the C2 by Br produce a chiral molecule which contain the prochiral center are called prochiral molecule and hence the phenomenon is called prochilarity. Retained an inversion of configuration. Whenever the chemistry reaction is carried out on the chiral molecule, the product may have the same configuration as reacted as a reagent or may be have opposite configuration. If the configuration of the reactant and the product is same, the reaction is said to be proceed with retaining of configuration. If the configuration of the product is opposite to that of reactant, the reaction is said to be proceed with the inversion of configuration. Two cases arise. First, when the bond to the stereo center or the chiral center is not broken, but the reaction takes place at the same another site in the molecule, the configuration of the reactant is retained in the product. Example, alcohol are converted into toric on treating with torus chloride in the presence of pyridine. When the bond to the osteocenter or chiral center is broken, either the inversion or retaining or configuration may be occur as discussed below. First, inversion. In SN2 reaction, the attack of mononucleophile always occurs from the direction of opposite to the leaving group. As a result, all the SN2 are accumulated by inversion the configuration. These phenomena was be discovered by Weldon and hence called Weldon inversion. Retained. The two important ways in which retaining of configuration occur are discussed below. For the SN2 occur at the same stew one after the another, the configuration of the final product is same as that of starting material. The retaining configuration hence has been explained on the basis of neighboring group participation in which the oxygen of the carbonate anion first help to eliminate Br in the SN2 reaction to form the alpha lactone. Second, which subsequently undergo the another SN2 reaction by the OH ion at the same stereocenter to afford the lactic ion with the complete retain of configuration if the reaction of first is carried out by the presence of strong alkyne solution or the hydroxide ion complete the carbonate anion and normally the SN2 reaction occur to give the lactate which with the inversion of configuration. Second, retention of the configuration may also occur if the bond cleavage and bond fusion occur on the same face of the chiral molecules. This is an example of an SN1 reaction. It also be suggests that the SN1 mechanism, like SN1 mechanism, can proceed by vice versa ion pairing as below. Racemic modification or racemic mixture. When the equal amount of an isomer are mixed together, it gives an optical active inactive form and called the racemic mixture or racemic modification. It is denoted by using the prefix positive, negative, or RS or DL before the naming of compound. For example, the equal amount of positive lactic acid and negative lactic acid are mixed together. We get the racemic mixture of positive negative lactic acid. A racemic mixture is always obtained whenever the critical compound or dissimilar compound is synthesized. A racemic mixture is always optically inactive because the rotation caused by the molecule of the one enantiomer are actually cancelled by the equal and opposite rotation caused by the same number of molecule of the another enantiomer. The other physical property of racemic mixture such as melting, boiling point, solubility is given solvent are different for those of an enantiomer. For example, the melting point of either enantiomer lactic acid is 3 to 6 K while the another racemic mixture is just 291 K. Racemization. The process of converting an enantiomer positive negative of optical active compound into the racemic mixture is called a racemization. Racemization is normal and undisable process and hence therefore any reaction is carried out on an optical compound. It is necessary to avoid the reagent or the condition which induce the racemization. Racemization can be occur either by heating chemical reagent, acid, base, or even contact with the polar solvents. So, of the most important mechanism by which racemic usually occur are discussed below. By rotation about the carbon-carbon single bond, optical activity of the ortho substitution diphenyl is due to the restriction rotation about the carbon-carbon single bond joining the two phenyl group. This the cause of this restriction rotation is the absence of bulk substitution at the ortho position of the two phenyl group, which prevent them in assuming the planar transition state. These compounds undergo the racemization on heating. Thus, when the particular anisomer or of an orthophenyl is heated, the heater is supplied over the energy barrier between the anisomer. As a result, the positive anisomer is converted into negative anisomer and vice versa. Immediately, a racemic modification result, for example, 6,6 dinitro diphennic acid racemized when heated by enolization. Optical active aldehyde or ketone have a hydrogen atom or a alpha chiral carbon atom under the racemization on treating with an acid or base. For example, acid catalyst ethanolization and base catalyst ethanolization. In this reaction, the racemization occurs through the intermediately of the planar ethanol and or the ethanate ion. The pronation of first and second at the either phase can occur with the equal probability to wild or racemic modification. For example, base catalyst racemization lactic acid to positive lactic acid has been shown below. By SN1 mechanism, racemization of optical active secondary halide such as 2-chlorobutane occur when treated with Lewis acid such as AlCl3. Under these conditions, the alkyl halide first undergo ionization by SN1 process to form a carbocation. Being the planar, the recombination of this carbocation with the halide ion can occur from either side of equal probability, resulting in racemization. The fourth is SN2 mechanism. The optically active halide having the halogen on the chiral carbon are also undergo the racemization by SN2 mechanism. For example, when the solubility of positive negative iodobutane is treated with NaI is in acetone, it undergo the racemization to give the positive negative 2-iodobutane. When the 2-iodobutane is treated with I negative ion, it undergoes the Waldine inversion to give the 2-iodobutane, which is the anisomer of first. Now the iodoform is undergo by Waldine process. Resolution. As stated above, a racemic mixture contains equal amount of two enantiomer. The process by which a racemic mixture can be separated into positive and negative enantiomer is called resolution. Since the enantiomer have identical physical and chemical property except toward the optical active reagent, they cannot be separated by a usually technology such as fractional distillation. In the unless the solvent are optically active, fractional distillation, chromatography, unless the absorption are optically active. Therefore, the special method are used to active their separation. Some of the important method to resolve the racemic mixture are discussed here. Mechanical separation. This is the most classical method and was used by the posture to separate the enantiomer of the sodium ammonium tetrate. Sometime when a concentration solution of a racemic mixture is allowed to crystallize, the two type of crystal may separate out. One type of the mirror image of the another. These Two type of crystal can be separated by the hand picking using a pair of trigger and magnifying glass and a microscope. Limitation: this method is important, most laborious and time consuming, and is applicable to only those compounds which give as well defined crystal of an enantiomer, so there we can be easily discussed. Biochemical method: certain microorganisms are used one enantiomer as their food, leaving out the other. For example, Penicillium gallicium consumed only by the positive tartaric acid. Thus, the racemic tartaric acid can be resolved by the addition of Penicillium gallicium to it, which consume positive tartaric acid and leaving behind the negative tartaric acid. Limitation: since one of the enantiomer is destroyed, this method is not satisfactory, and further, this method cannot be used to separate poisonous compound which may kill the microorganism. Chemical method: this is the most widely used method for separation of racemic mixture. This method is based upon the principle that means when a racemic mixture is treated with an optical active reagent, it give a mixture of this enantiomer. Since this enantiomer are mirror images of each other, they cannot be physical properties such as melting point, boiling point, solubility, and etc. Hence, we can be separated by the physical methods such as fractional distillation, fractional crystallization. After the separation, each then dienostomer is decomposed separately to give a mixture of corresponding enantiomer and the optical active reagent. The optical active reagent is then removed by the suitable metal, leaving behind the pure enantiomer. To isolate this method, let us consider the resolution of positive tartaric acid when the treated with the optical active base such as positive buricine. Positive negative tartaric acid give a mixture of two this stereoisomer. The positive tartaric acid and positive butane and the negative tartaric acid and positive butane, these two compounds will be this distomer and have widely used solubility and hence are separated by frictional crystallization. After the separation of this distomer is purified by the resolute crystallization and treated separately with the dilute HCl to generate the corresponding positive negative tartaric acid. The whole process is schematically shown below. Positive negative tartaric acid buricine. Positive negative tartaric acid buricine plus negative tartaric acid plus positive butane separated by the crystallization process. Similarly, the positive base can be separated by using the n-optical active acid such as tartaric positive or the minus malic acid. Chromatography. The racemic mixture can also be separated by column chromatography using an optical active observance such as starch, lactic. When one of the enantiomer gets absorbed, evolution of the column with the suitable solvent first give the enantiomer which is not absorbed strongly, and subsequently the more strongly absorbed enantiomer. In this way, the desired separation is achieved. D, L, and R as nomenclature related and absorbed configuration. The argu- argument of the atom or group of atom which categorize a particular skewer are called configuration. Two terms which are commonly used to describe the configuration of the different skews are absolute and relative configuration. By the absolute configuration, we can mean actual arrangement of atom group in a space of a particular skewer of a compound. The relative configuration, on the other hand, means the arrangement of atom group of a atom in a space of stereoisomer of a compound related to the atom or a group of atom of another compound chosen as a arbitrary standard. It is if the absolute configuration of the standard is established by some unambiguous method, then the relative configuration of the stereoisomer colligated in fact represent its absolute configuration. Considered for this lactic acid, it exists as a pair of anisomers. First, second, each of these anisomers has a different configuration about the chiral center. One of these is the extraordinary and while the another is laboratory. How do you know which is which? To solve this problem, organic chemistry has been developed two different conversation as given below. The D and L nomenclature or DL system. Before the 1915, there will be no method available for determining the absolute configuration of a compound. Therefore, the relative configuration of all the compound will be established, written by glyceric acid chosen as a alternatory standard. The two anisomers of these compounds were be designed by L and D and L symbol. The positive enantiomer will be give the symbol of the where was assigned to the configuration third in which OH group is lie toward the right and the hydrogen lie toward the left. The CHO group lie at the top and the CH2O lie at the bottom of the Fischer projection. On the other hand, the negative glyceric acid can be given by the symbol L and was be assigned to be configuration 4 in which OH group toward the left and H group toward the right. Relative configuration of the compound were then established as follow. Any compound that can be prepared from or converted into D plus glyceric acid will be belong to D series, and similarly any compound which can be prepared from or converted into L negative glyceric acid will be belong to the L series. These calculations are based upon the general principle that if a reaction does not involve the cleavage of the bond to the chiral center, the configuration about the chiral center is retained. For example, D-glyceric can be converted into negative glyceric acid by the simple oxidation, and hence the configuration of glyceric acid is obtained by D. Similarly, the positive lactic acid obtained from the L negative glyceric acid by the following sequence of reaction assigned the L configuration. Although the configuration assigned by the Fischer to D and L were be purified arbitrarily at that time, but constantly in 1951, the X-ray diffraction study of on sodium ribosome tetrate by the Bizuweit proved that they were in fact correct. Thus, the relative configuration D positive glyceric acid and positive lactic acid dissolved above in the fact represent the absolute configuration. The flowing, the above producer the absolute configuration of large number of optical active give the compound have been established. If it may be noted that there will be no simple relation between the absolute configuration of a particular enantiomer, its direction of rotation, planar light. In another word, the compound having the same configuration may be have different sign of rotation. Example: D glyceric acid and D positive glyceric acid and D negative glyceric acid have the same configuration but different sign of optical rotation. Similarly, the compound having different absolute configuration may be have the same sign. For the example, Leo negative glyceric acid and D negative lactic acid have opposite configuration but have the same sign of rotation. For the compound containing the several chiral carbon atom, the configuration at the one stereocenter is related to with the glycic acid, while the configuration of the another stereo are determined related to with first. In the case of glyceric stereo, at the penalty carbon atom C5 is correct correlated to the glyceric acid, while the configuration of the another stereo can be determined related to the first. Since the nature of occurring glucose, the OH group at C5 is assumed to be toward right is designed as the D glucose. Limitation. First, sometimes the same compound have been colligated by the sequence of reaction to be known as D compound by the different sequence of the reaction to known as L compound. This method is quite cumbersome to apply to such compound which contain two or more chiral carbon atom. Because of these difficulties, D and L system is seldom used these days except with the carbohydrates and amino acid. RS nomenclature absolute configuration. The limitation of the system has been RS nomenclature absolute configuration. The limitation of the DL system have, however, been removed by the unambiguous system developed by the RS Chan, CS Ingold, and V prelogue are called Chan Inlow prelogue system and simply the RS system. The designation of the absolute stoichiometry of this optical compound according to the system involved the following step. First, priority number such as 1, 2, 3, 4 is assigned to each of the four atom or the group of the atom attached to the chiral compound is accordance with the following sequence rule. Sequence rule first. If the force substitute attached to the chiral compound are all atoms, their priority number are decided on the basis of atomic number. The atom of higher atomic number get higher polarity. Thus, the compound bromochloroiodomethane, the order of decreasing priority. First, ido first, bromo second, chloro third, hydrogen fourth. If the two atoms attached to the chiral carbon are isotope of the same element, the isotope of higher mass get higher priority. For example, in the compound of alpha deuterethyl bromide, the order of decreasing polarity is Br first, C H3 second, D third, H4. Sequence rule 2. If the relation of the polarity of the two groups attached to the chiral carbon cannot be decided on the basis of rule 1, it may be decided by the comparing the atomic number of the next atom in the group and the S of the if the necessary work outward from the chiral compound to the first point of the difference. In the another word, in the first atom attached to the chiral center is same as in the both the groups. Compare the atomic number of the atom attached to the first and consider the example of 2-butanol. The first two atoms attached to the chiral carbon are themselves carbon atom and in the CH3 group the second atom of HHH while the CH3 CH2 group which have the CHH and hence the C is higher atomic number than the H and the CH3 CH2 group have higher priority over the CH3 group. Thus, the complete sequence of priority of 2-butanol is therefore OH first, CH3, CH3, CH2 second, and CH3 third, and H fourth. The sequence rule third, the double bond and the triple bond are treated as if they have duplicated or triplated single bond. In the another word, each doubled bond atom is duplicated and each triple bond atom is duplicated. Thus, to isolate this, it let us glycoaldehyde and 3-chloropentane are as example. In glycoaldehyde, OH has the highest priority of all the substitute and the OOH of the CHO have great priority over the OHH of the CH2OH. This is complicated sequence of the priority is OH first, CHO second, CH2OH third, and H fourth. A phenyl group C6H5 is considered if it had one of the Kekule rule structure. Comparison of priority of phenyl, acetyl, vinyl, and isopropyl group. In order to assign the priority of each of these groups, let us consider the number and nature of the atom attached to the first carbon in each case. In phenyl and acetylenic group, the first carbon is connected to the three other carbon atom, while in vinyl and isopropyl group, the first carbon is attached to only the two carbon atom. Therefore, the phenyl and any acetylene group has higher priority over the vinyl and propyl group. To decide the relative priority of the phenyl and acetyl group, we must proceed the further among the chains. In the phenyl group, two of the CCC are further connected to CCH, while the three is duplicated carbon. On the other hand, it is acetonic group. Only one of the CCC is further connected to CCH, while the other two are duplicated carbon. Therefore, phenyl group get higher priority over the acetylene group. To decide the relative relation and decide the relative priority of the phenyl and iso group, let us consider the nature and the number of atoms attached to a second carbon. In vinyl group, the second carbon is connected to one carbon duplicated and two hydrogen atom. But in isopropyl group, the second carbon is connected to over the hydrogen atom. Therefore, the vinyl group take a priority over the isopropyl group. Thus, in the light of the above discussion, the complete priority sequence is C6H5 have greater and C double bond CH and CH double bond CH2 CH have triple bond. Steps 1. Once the order operator of the four atom or group are directly attached to the chiral carbon has been decided, the molecule is then alternated in the space such as a way that the group of the lower priority is directed over from us. A good analysis of the situation in this sterling wheel of a motor car within the group of the lower priority represent the steering rod, and the three other atom or group represent the three spoke of the wheel. If the going from the group of highest priority to the group of second priority and then to the group of third priority, first second third I moving of the clockwise direction, the configuration is specified as R, and if the anti-clockwise, the configuration is specified as assignment of R and S configuration to the Fisher projection. The assignment of RS configuration to the Fisher projection of organic compound involved the following steps. Step first, assign the priority to the four atom or group attached to the chiral compound. Second, if the atom or group of the lower priority occur the horizontal position left or right in the Fisher projection formula of organic compound, then make two interchange of the atom or group in such a way that the atom or group of the lower priority is placed either the vertical upward or downward. It is done by flowing method. The example isolated above. First is glyceric acid, second is 2-butanol. Assignment of R as configuration to the Fisher projection containing two chiral carbon. When the compound containing two different chiral carbon atom, four different stew are possible having the following configuration: 2R, 3R, 2R, 3S, 2S, 3R, 2S, 3S. The following step is discussed in the section 3.4.21 above. Each chiral center is separately assigned of R and S configuration. Let us assign the R S configuration to second and third in the positive tartaric acid. Thus, the configuration of positive tartaric acid is 2R, 3R tartaric. By knowing the configuration one of the stereo, the configuration of the other two can be predicted easily as shown below. It may be noted that the direction of the rotation of the plane polarity light has nothing to do with R and S notification, while giving the other direction in which the eye travel when we visualize a molecule held in a arbitrary manner. The R and S compound may be either dextrorotatory or levorotatory. The method discussed above is quite time consuming. Therefore, a simple rule has been formulated to assign the RS configuration to the chiral center in organic molecule shown in 3D or Fisher projection. This is called the golden rule, and discuss below. Golden rule: assign the polarity to the four carbon or a group attached to the chiral center without making two interchange of the atom or group. Find out the configuration. If one of the atom or group of the lower priority verify occupy the vertical position in the Fisher projection, then the configuration obtained above give the actual configuration of the molecule. If the however the atom or group of the lower priority occupy the horizontal position in the Fisher projection, then the change the configuration from R to S or vice versa. For example, R without making the two interchange, the configuration turn to R, and since the lower priority R H occur vertical position in the Fisher projection, therefore correct configuration of compound remain to R. Without making the two interchange, the configuration turned to be R, and since the atom of the lower priority H lie in the horizontal position in the Fisher projection, therefore R to S, and thus the correct configuration rotation of the compound to S. Simple method for converting the flying wedge of or 3D formula to Fisher projection formula. The atom or group shown below on the plane of the paper is kept at the bottom of Fisher projection formula, and remain three atom group are arranged in the same sequence as they appear in flying wedge formula. For example, let us convert the flying wedge formula first into the Fisher projection formula. Second, since the CH3 is below the plane of paper, it is placed at the bottom of the Fisher projection second, and the remaining three group of OOH, H and COOH are in the anticlockwise sequence, and hence they are arranged in the sequence in Fisher projection. Second, theoretical more than one Fisher projection formula can be written for any given chiral compound. Therefore, to get the most conventional Fisher projection formula in which the vertical projection of the portion of the projection interchange of the atom group attached to the chiral compound. For example, thus the Fisher projection of second, third, and the flying wedge formula of first old lattice acid. Thus the wedge formula of fourth and the Fisher projection formula of fourth and sixth all represent the R glyceric acid. Simple method for converting the Fisher projection formula to flying wedge formula or 3D formula. The atom group which is at bottom of the Fisher projection formula is kept below the planar of the paper in the flying wedge formula, and the remaining three atom or group are arranged in the same sequence clockwise and anticlockwise as they appear in the Fisher projection. Keep one of the atom or group lying on the horizontal axis in the Fisher projection formula above the plane of paper in the flying wedge formula. Please note that the sequence of all these atoms in both of the formula shown be same. For example, to test whether the flying wedge formula second actually represent the R lactic acid, we make it interchange of the atom and group in a such a way that the atom of the lowest priority lie below the plane of the paper, and assign the priority to the four atom group attached to the chiral center. You may be find that the formula of third and hence the formula of second actually represent the R lactic acid. For the further isolation, consider the Fisher projection formula of S2-butanol 4. Here, the Fisher projection formula and the flying wedge formula 4th and 6th are represented as S2-butanol. Geometrical isomerism. Like the optical isomerism, geometrical isomerism are also configurational isomerism, since they are interconverted only by breaking and remarking the covalent bond. Further, since the Geometrical isomerism are not mirror image of each other. They are not an isomer, but the configuration isomer which are not mirror image of each other and are called distinct isomerism. Therefore, the geometrical isomerism may be regarded as an distinct isomerism. Some important examples of the kind of distomer are discussed below. Geometrical isomerism hindered rotation around the carbon-carbon double bond. We know that the double bond consists of pi bond and sigma bond. The pi bond is formed by sideway overlapping of unhybrid p orbital of two carbon atoms above and below the plane of the carbon. If one of the carbon atom of double bond is rotated with respect to the other p, there is no longer overlap and pi bond should be break. But the breaking of pi bond required 251 kilojoule mole inverse of energy, which is not provided by coagulation of the molecule at room temperature. Contrarily, the rotation of the carbon-carbon double bond is not freely but strong, hindered and restretched. In another word, the pi bond prevent the free rotation of carbon atom of double bond with respect to each other. Due to this inherent rotation, the relative position of the atom group attached to the carbon atom of double bond are fixed. For example, HAHB in the figure 3.25 cannot be exchanged their position by rotation of C1 with respect to C2 without breaking the pi bond. As a result, many substitute alkane can be exist in two distinct isomerisms which are different from each other only in the relative position of the atom or the group in the space around the double bond. For example, butene can be exist in the following form: first and second. Both of these isomers have the same structure formula but different in relative spatial arrangement of the hydrogen atom and methyl groups around the double bond. Such isomers which have the same structure formula but different in relative or spatial arrangement of the atom or group around the double bond is called geometrical isomerism, and the phenomena is called geometrical isomerism. This is Thus, the geometrical isomerism is a type of space or stereoisomerism. The isomerism first in which two similar atom or group lie on the same side of the double bond is called the cis, while the second in which the similar atom lie in the opposite side are called trans isomer. This is because the reason the geometrical isomerism are also called cis and trans isomerism. Necessary and sufficient condition for the geometrical isomerism. It may be mentioned here that all the compound containing carbon-carbon double bond do not show geometrical isomerism. The necessary condition for alkene to exist geometrical isomerism is that each of the two carbon atoms of double bond must have different substitute which may be same or different. Thus, the alkane of type ABC double bond CAB and ABC double bond DE show the geometrical isomerism. However, the geometrical isomers are not possible if one or both double bond carbon atom carry two similar substitutes. This is because in such cases two possible configurations in fact identical as shown below. It is because of this reason that the terminal alkanes such as propane, but1-ene, 2-methyl prop1-ene and the alkene carrying the identical substitute on one of the double bond carbon atoms such as 2-methyl but2-ene and 2,3-dimethyl but2-ene do not show the geometrical isomerism. And determination of configuration of the geometrical isomerism. We have discussed above that the disubstitute alkane carrying two different substitute on each of the two carbon atom of double bond exist in the stereoisomerism form cis and trans. Now the question arises, how do these which is represented distance between this pair of isomerism can be easily made on the basis of difference in the physical and chemical properties are as discussed below. On the basis of their physical property, melting point in general, the melting point of trans is higher than the corresponding to cis isomerism. In trans isomerism, the two similar atom or group lie on the opposite side of the double bond. Cis isomerism had two similar atoms or group lying on the same side of double bond. Therefore, these molecules are unsymmetrical and hence do not pack well in the crystal. As a result, the intermolecular force of attraction held by the molecule for trans in the crystal length is much stronger than the holding molecular force of cis. Consequently, the melting point of the trans is higher than the cis. Solubility. In general, the solubility of cis is higher than the corresponding trans. This is due to the reason that the molecule of cis are weakly held in the crystal that the corresponding trans, as explained above. Tux. Dipole moment. In general, cis have higher dipole moment than the corresponding to trans, which may be even zero dipole moment when the atom or group on each carbon atom of the double bond are seen. This is due to the reason the cis isomer, the two dipole are inlined to each other at the angle of approach 60 degree and hence has a finite dipole moment. On the other hand, trans have two dipole act as opposite direction and hence cancel each other for each other. It may be, however, be noted here that the trans isomer need not necessarily have to be zero dipole moment. For example, the trans pentene have finite dipole moment through a smaller than the corresponding cis isomerism. This is a reason being that dipole moment of the CH3 and the CH2 CH3 bond have not equal. Although these two dipole opposite of each other do not exactly cancel out by each other and hence trans pentene has a small finite dipole moment and trans pentene is much lesser polar than the cis pentene. Boiling point. In general, boiling point of cis is higher than the trans. This is the reason that why the boiling point of the cis compound depend on dipole moment of interaction. Since the cis have the high dipole moment than the corresponding trans, therefore the boiling point of cis is higher than the boiling point of the trans. On the basis of their chemical reaction, the formation of cis compound. These methods are more dependable on that the physical method in the cis isomer, the reaction group being on the same side of the double bond and interaction with each other result in formation of cyclic compound. On the other hand, the trans has isomer, the reaction group has been on the opposite side of the double bond and do not interact with each other to form a cyclic compound. The malic acid on heating with 423 liter above the melting point really lose a molecule of H2O to form a malic anhydride on heating anhydride to give a COH group and nearly each other. However, as a temperature of furic acid malic anhydride, the two COH group nearly to each other. However, at this temperature, furic acid trans isomer does not form an anhydride since the two COH group are far apart. And however, when the furic acid heated to 573 closer to the melting point, it loses a molecule of H2 to give a same anhydride. Malic anhydride on hydrolysis give a malic acid, do not form the formic acid. On the basis of optical property, the stereoisomer formed during the hydrolyzation and bromonization reaction. Optical property of a product formed depend upon the stereochemistry of the reaction. Since the hydroxylation of alkane with dilute KMnO4 solution or osmium tetraoxide and sodium bis sulfide treat is cis addition process. Therefore, the cis isomer give the messy product while the trans give the racemic product. For example, malic acid in the presence of dilute aqueous KMnO4 give the mesoteric acid, whereas fumic acid in the presence of dilute aqueous KMnO give the tartaric acid, positive tartaric acid. That is a racemic mixture. In contrast, the bromization of alkane is trans addition process. Therefore, the trans alkane give the meso product while the cis give the racemic product. E and Z system of nomenclature. We has been seen the cis and trans notation can be used without any to describe the specular originated of the identical atom or group around the double bond is discrete alkyne. However, in the case of tri or tetra substitute alkane, in which three or four different atoms or group can be attached to the carbon atom of double bond, it is difficult to assign the cis and trans notation to a pair of geometrical isomerism. To isolate this, let us consider the following geometrical isomer of 1 bromo, 2 chloro, 2 fluoro, 1 iodoethane, in which the four different atoms are attached to the double bond carbon atom. If we say that Br and Cl are trans to each other, we can also say equally accurate that iodine and chloro are cis to each other. Therefore, it is difficult to name such substance either as cis and trans. In order to avoid this ambiguity, a major general system of nomenclature for destination of the configuration isomer about a double bond has been developed. This is called EZ system and is based upon the priority sequence rule of the original development by the Canon, Gold, and Prelong to describe the configuration about the chiral center in a molecule. The main point of E and Z system are discussed below. Flowing of the sequence rule describe the optical active compound RS system in the section 3.4.20. A priority order is assigned to the atom or group attached to the carbon of double bond. Second, if the atom or group of higher priority on each carbon atom of double bond are on opposite side of the double bond, the configuration is designed to be E. If on the other hand, the two atom or group of high priority on each carbon atom double bond have the same size, they are configuration designed to be Z. From the German word Tux, let us isolate these rule flowing example. First, two geometrical isomer of 1 bromo, 2 chloro, 2 fluoro, 1 iodoethane are. Since we know that atom of higher atomic number have the higher priority, as the higher priority than Br and at carbon first, and Cl has the higher priority than F on at the carbon second. The isomerism first with the atom of high priority iodine and chlorine being at opposite side of the double bond is designed as E isomer, while the isomer of second which of these high priority on the opposite side of the double bond is assigned as Z isomer. Cis and trans isomer of 2-butane can be designed as Z and E2-butane respectively. Here, the CH3 has higher purity than the H since the atomic number of the carbon is higher than the hydrogen. Similarly, the malic acid and fumaric acid may be designed as E and Z isomerism. Geometrical isomerism in the compound containing two or more double bonds. If the compound have two double bonds in which the end are different, then the four geometrical isomerism are possible. In another word, the geometrical isomerism is 2 की power n, where n is the number of double bond. It may be noted here that this formula apply only to those molecules in which the two ends are different. If, however, the two ends are identical, then the number of geometrical is first 2 की power n minus 1 plus 2 की power n by 2 minus 1, where n is even. Geometrical isomerism in oximes. Oximes are the compound formed by the action of hydroxyamine on aldehyde and ketone under the weakly acid condition. In terms of modern theory of valency, both the carbon and nitrogen atom in oxime is sp2 hybridization. Thus, similar in the hybridization of carbon atom in the ethylene, hence the C double bond and bond like that C double bond O can consist of the pi bond and the one alpha bond, and the 3sp2 hybridization nitrogen contain a lone pair of the electron. Thus, the oxime molecule is coplanar above the double bond and the alkane exhibits the geometrical isomerism due to resistant rotation about the C and double bond. However, here the prefix SY for cis and NT for trans more commonly used in the case of aldoxime. Cis isomer is OH lie on the opposite side of the double bond. Example. In the case of keto isomer, the prefix SN and NT indicate the relationship between first group name and the hydrolyzed group tux. Oxime can also be named by the EZ system of nomenclature as shown above. Here OH is also assigned to priority first, while the atom or the group on the carbon atom assigned priority first second in accordance with the sequence rule discussed earlier in the section 3.420. Determination of the configuration of oximes. Aldoxymes. Aromatic oxime exhibit in the two geometrical isomer form called the sine or antiform. Alphabetic aldoxime exists only in one form, the more stable antiform. The configuration of aromatic aldoxime are determined by the first converting them into corresponding acetyl derivative on treating with the acetyl aldehyde in the presence of trace of the acid, then treated with the aqueous solution of Na2CO3. If one of such a treatment, the original oxime is regenerated, the oxime is designed as E or the cyanic isomer, and however, if the molecule of acetic acid is lost from an array cyanide, the oxime is called the Z or anti-isomer. Ketoisomer. The configuration of the geometrical isomer aromatic ketoxime alphabetic ketoxime occur only in one form are determined by the Blackman rearrangement. The ketoxime is treated with an acidic reagent such as PCl5, H2SO4, SOCl2, etc. When the oxime isomerized into a substitute amide by migration, the group which is anti to the OH and the structure of amide tugs formed are determined by the hydrolysis to the corresponding acid the amide known structure of the acid and the amine tux form. The configuration of enzyme is established tux. Geometrical isomerism in acyclic compound. We have discussed about the geometrical isomerism are due to registration rotation about a bond in the principle such as in hertz should be noted the registered to double bond only. For example, acyclic compound with C 3 to 6 membered ring such as distinguished and derivative of cyclopropene, cyclobutane, cyclopentane and cyclohexane because of their result ring structure also show the hindered rotation about the carbon-carbon single bond and hence exhibit the geometrical isomerism. To understand the geometrical isomerism more clearly, we can assume the carbon atom of the ring form a planar ring as shall be later in this unit. This plane of the ring is usually drawn horizontally and the edge of the ring projection toward a shadow heavier. The substitute at each carbon of the ring are given by vertical line. When the atom or group placed at the top of the vertical line is said to be have the above plane of the ring, and when the atom or group is placed at the bottom of the vertical line is said to be below the plane of ring. Sometimes the broken wedge is given to indicate the group below of the plane of the ring and the solid line of the above the plane. For isolation geometrical in acyclic compound, consider the following example. Discrete cyclobutane, cyclopentane showed the two position isomerism, each one of which can discuss geometrical isomerism. In contrast, the substitute cyclohexane has three position isomer, each of which can be exhibit geometrical isomerism. For example, configurational isomerism. We have already discussed in the first that the sigma bond between the two carbon atom is formed by overlap of sp3 hybridization orbital of each carbon atom and their internuclear axes. Therefore, the electron discussed within the molecular orbital tux formed is cylindrical symmetrical among the internuclear axes as shown in the figure 3.26. Due to this cylindrical symmetry of pi m rotation about the carbon-carbon single bond is almost free. As the result, the almost free rotation, the molecule of alkane can be differentiated and different relative arrangement of their atom in the space. This infinite number of momentary arrangement of atom in the space which result to rotation about a single bond is called configuration or rotationally isomerism. Simple rotatory. Let us apply the concept of free rotation about the carbon-carbon single bond to alkanes such as ethane, propane and butane molecule. Discuss their configuration. Configuration of ethane. In ethane, the CH3CH molecule has two carbon atoms are connected by the pi bond. If one of the methyl group is ethane molecule, it gets fixed and another rotate to the C bond. A large number of momentary arrangement of hydrogen group on one carbon represent two hydrogen atom on the another carbon in a space are obtained. These infinite number of momentary arrangement of atom in the order carbon atom in the space are obtained. Thus, a finite number of momentary atoms in the space represent the configuration of ethane. In all these configurations, the basic structure of ethane molecule and various bond angle and bond length are remain same. Out of the infinite number, the possible configuration of ethane, only the two extreme one are important, and these are called segregated and explicit configuration. Two-dimensional Configuration. Three-dimensional structure can be represented on the two-dimensional surface by the help of Fisher projection. One serious drawback of this projection formula is that they represent the molecule of unfavorable explicit configuration. However, while the discussion the reaction of the molecule, it is unusually described to the despite the molecule, it is actually segregated form rather than the hypothetical expelled form as shown in the Fisher projection. Therefore, to overcome the difficulty, the configuration of molecule are usually represented by the flowing tree method. First, show horse formula. This is simple method of representing the three-dimensional formula on the paper. The molecule is viewed slightly above and from the right and projected on the paper. The bond between the two carbon atoms is diagonal and is slightly elongated for clarity. The lower left hand carbon is considered to be toward the front and the upper right hand toward the back. The show horse representation of segregated and ascribed configuration of ethane are shown in figure 3.20 and flying wedge representation. In this formula, the bond connected the two carbon atoms are drawn horizontally in the plane of paper, and wedge represent the bond lying above the plane of paper. Ordinary lines are used to denote the bond lying within the plane of paper. The dotted line stand for the bond lying below the plane of paper, and the flying wedge represent the for the segregated and explicit the configuration of ethane as shown in figure 3.28. Newman projection formula. Newman drive a simple and highly useful method for represent the three-dimensional formula on the paper. After this name, these are called Newman projection. These projection formula are obtained by viewing the molecule along with the bond joining the two carbon atom. The carbon atom near the eye is represented by the point, and the three atom or group attached to it by the three equal spaced radii. The carbon atom further from the eye is discussed by a circle, and the three atom or group attached to these equally spaced radical expansion. The Newman projection of the segregated and explicit configuration of ethane are shown in the figure 3.29. Relative stability of segregated and explained configuration of ethane. In the segregated configuration, each of the hydrogen atom on the front carbon lie actually in between each of the hydrogen atom on the back of the carbon. In another word, in this configuration, any two hydrogen atom on the adjacent carbon atom non-bonded hydrogen are so far apart as possible. The internuclear hydrogen and 2 hydrogen is equal to 3.1 nanometer. As a result, the repulsion between the electron cloud of pi bond of the two non-bonded hydrogen atom is maximum. On the other hand, in the X-spaced configuration, each of the hydrogen atom on the back carbon lie externally behind each of the hydrogen atom in the front of the carbon. In other words, the non-bounded hydrogen atom are quite closer. As a result, the electron cloud of the pi bond of two non-bonded hydrogen atom repel each other, and this rise the energy of the applied Explicit configuration related to the segregate configuration. Thus, the segregate configuration of the ethane should be more than the explicit configuration. Experimentally, it has to found to be so. The segregate configuration of ethane is about 12.55 kilojoule more stable than the explicit configuration. The variation of the energy of the configuration of the ethane with the rotation about the carbon single bond is shown in figure 3.30. The energy difference of 12.55 kilojoule per mole between the segregate and explicit is in fact the energy barrier to rotation about the single bond in the ethane. However, the energy barrier is not large enough to prevent the rotation. Even at room temperature, the collision of the molecules simply sufficient the kinetic energy to overcome this energy barrier. Thus, the two configurations are really inconvertible. As a result, it is possible to separate the two configurations of ethane, and however, at any given moment, most of the ethane molecule would exist in the segregate configuration due to the minimum energy and maximum stability. Second concept, configuration of propene. Propane contains three carbon atoms linked in one another by a single bond. In order to study the configuration of propane, let us consider it derivation of ethane in which one hydrogen atom replaced by a methyl group as shown below. If one of these carbon atom is fixed and another is rotated around C1 and C2 carbon bond through an angle of 360, at infinite number of configurations are theoretically possible. Out of these, only two extreme configurations, segregated and explicit, are important. The new line projections are shown in figure 3.31. Like the ethane, the segregate configuration of propane is more stable than the explicit configuration. The energy difference between these two configurations is 14.2 kilojoule mole, which is slightly more than that in ethane. Even then, this energy barrier to rotation about the carbon-carbon single bond is so small that it cannot prevent the rotation. As a result, the two configurations are readily convertible. Thus, it is more possible to separate their two configurations. Just like the ethane, the two configuration of propane can be interconvertible by rotating through the angle of 60 degree. Configuration of N-butane. In order to examine the configuration of N-butane, it is considered as derivative of ethane in which one hydrogen atom of each carbon is replaced by the methyl group. Thus, butane is considered as a dimethyl ethane as shown below. Thus, each of the two center of the carbon atom C2 and C3 in the butane is linked by one methyl group and two hydrogen. If now one of these carbon atoms is fixed and the another is rotated around the center bond at the angle of 360, an infinite number of configurations are theoretically possible. Out of these, 6 configurations are important. Their Newman projection are given in figure 3.32. In the configuration first, the methyl group of the two hydrogen atom are on C2 are exactly behind the methyl group, and the two hydrogen atom of the C3 represent. This is the fully explicit configuration, and dehydrate angle for the configuration is 0 degree. When the configuration first is rotated and the angle of 60, the gauge's configuration second result the rotation through the 60. The product explicit configuration, which is different from the fully explicit configuration, further rotation through 60 degree give to the completely or fully segregated configuration. Fourth, this is also called the anti-configuration. Further, the rotation through 60 gives another explained configuration fifth, which is similar to the configuration third. Still, the further the rotation of 60 degree gives another Gauss configuration similar to second. Finally, if we rotate the configuration fourth by 60, we retain the fully explained configuration first. The completion rotation of 360 we around the C2 and C3 bond tucks the form of the above discussion. It is followed that N-butane has four distinct configuration: anti-configuration, Gauss configuration of second and fourth, escape configuration of third and fifth, and fully expand configuration of first. There are relatively potential energy as shown in figure 3.33. Relatively stability of the configurational of N-butane. Out of the four distinct configuration list above, anti-configuration is most stable since in each of the configuration has two non-bonded methyl group dihydrogen angle is 180 and four non-bonded hydrogen atoms are far apart as a possible. The next in order of higher energy are come the two garage configurations second and fourth, in which the two non-bonded methyl group are only 60 degree above since cause the crowding or streaky strain. As a result of this, the streaky strain, the two garage configuration second and fourth are slightly less stable than the anti-configuration fourth. However, the gas configuration are themselves of equal energy. Experimentally, it has been found that the gas configuration are about 3.35 kilojoule mole per liter less stable than the anti-configuration. Next, in order to of higher energy fall into the two particle escape configuration, third and fifth. In this configuration, there are two methyl hydrogen explicit interconnecting and one hydrogen hydrogen explicit interconnecting. Since each methyl hydrogen explicit interaction introduce an energy of 5.85 kilojoule mole per and each hydrogen hydrogen explicing interaction and introduce an energy of 3.35 kilojoule mole. Therefore, the particle excrete configuration of N-butane are less stable than anti and garage configuration. However, the two particle excrete configuration are themselves of equal energy. Experimentally, it has been found that particle excrete configuration third or fifth is less stable than the Gauss configuration second and sixth by about 10.85 kilojoule mole and their anti-configuration fourth by about 14.2 kilojoule. The fully expelled configuration first is, however, the least stable, and this is due to the reason that the configuration there is one solvent methyl expelled interaction and two weak hydrogen hydrogen expelled interaction. Experimentally, it has been found that the fully expelled configuration is about 18.4 to 25.5 kilojoule less stable than the most stable anti-configuration. The relative stability of the four distinct configuration of N-butane follow the order of anti-garage or stick and then particle explicit and fully explicit. Since the energy difference between these is very small and can be easily supplied by the collision of the molecule at room temperature. Therefore, these four configurations of N-butane, like of those of ethane, are really inconvertible and hence hence cannot be isolated. Further, since the energy difference between anti and Guerre's configuration is much smaller, which then between the anti-particle expelled, Guerre's particle expelled and anti-fully expelled and Guerre's fully expliced configuration. They most of the molecule at room temperature express and fully expressed configuration to the equilibrium in most of the negligible. The experimentally, if the configuration while one third of the molecule exists and the little less stable Gauss configuration with negligible or non-contributable for a particle or fully explained configuration. Such segregated configuration gas and anti which have minimum or near minimum energy are obtained referred as configurational isomer and simple conformer. Conformation of ethylene glycol. Like and butane, ethylene glycol can exist in the following four distinct configuration. In the case of n-butane, segregate and or anti-configuration is the most stable. However, in the case of ethylene glycol, the intermolecular hydrogen bonding is possible in the garage configuration, but not in the segregated form. This would be stabilize the molecule by about 20 to 29 kilojoule mole. Therefore, the Garage configuration of ethylene glycol is the most stable. Likewise, because of the intermolecular hydrogen bond, the Garage configuration of ethylene chlorohydrin is more stable than the Garage configuration. Configuration of 1,2 dibromoethane. Like the butane and ethylene glycol, 1,2-dibromomethane can exist in the following four distinct configurations. As the antiseptic, the Garrett configuration of first and second dibromide methane is most stable, followed by Garage and dipole moment of the segregated configuration is zero. Hence, the two carbon bromine dipole are equal and opposite. However, the Garage configuration has finite dipole moment, and since the two carbon bromine dipole are inclined by each of other at a angle of 60 degree. Since the actual dipole moment of first and second bromomethane is 1d and the molecule cannot be externally in the segregated form. Further, since the dipole moment vary with the temperature, the molecule cannot be exist internally in the Garage form either. To explain this experiment result is assumed that there is an equilibrium between the gas segregated and the Garage configuration, and with increase in temperature the equilibrium shift in the behavior of Garage configuration, hence the dipole moment increase with the temperature. Configuration of cycloalkane. Like the cycloalkanes show the configuration isomer. So, the cycloalkane and cyclobutane are planar molecules with the bond angle are planar molecule with bond angle of 60 and 90 respectively, but the normal tetrahedral angle is saturated compound of carbon in 109 degree. Thus, the bond angle of the cyclopropane and cyclobutane are quite different from normal tetrahedral angle. This derivative form the normal tetrahedral angle introduce constantly angles strain in the molecule of these cycloalkane. Further, greater the derivation, more the strain in the molecule and hence more the reactivity in these compound. For example, cyclopropane with a bond angle of 60 is much very strained and hence very reactive. Cyclobutane with a bond angle of 90 is less strained and hence it is more stable but reactive than the cyclopropane. In the cyclopentane, the bond angle is 180, that of regular pentagon. which is very closer to the tetrahedral angle of 109 degree. As a result, it has very little strain and hence it is quite stable and less reactive than the cyclopropane and cyclobutane. Further, the cyclopentane has been shown to have unknown planar configuration. Although for all the practical purpose it is considered to be planar. On the other hand, the Sacreus and Moore in the 1890 suggest that the cyclohexane has two planar, non-planar or puckered configuration called the chair or and the boat configuration as in the figure 3.35. The name chair and the boat are used for this configuration because of their resemble to a lane chair and a boat respectively. It may be noted here that both these configurations are freely from angle strain and hence are quite stable and unreactive. Reactive stability of chair and boat configuration. Although both the chair and boat form are free from angle strain wet, the chair form is more stable than the boat form because of the following two reasons. In the chair form configuration, all the carbon-carbon and carbon-hydrogen bond as shown in the figure 3.36. As a result of this segregated nature bond, the chair configuration of cyclohexane is not free of the angle strain and total strain but free of the steric strain as well. On the basis of, on the another hand, in the boat configuration, though through the carbon-carbon and carbon-hydrogen bond on the and is segregated oriented, and those of C1 and C6 and C3 and C4 are in the contrast to the chair form and has considerable and torsional strain as well as steric strain. Although like the chair form, it has no angle strain constantly. The boat form of the cyclohexane should less stable than the chair form. Second, boat form of the cyclohexane is further destabilized by the steric strain between the non-bonded hydrogen atom. These flagpole hydrogen atoms are separate from each other by a distance of about 1.85 or 1.3 picometer. At a distance considerably less than the sum of these van der Waals forces of radius 2.29 and 229 picometer. As a result, the electronic cloud of these bonds repel each other, therefore further raising the energy content of the both form. Other configuration of cyclohexane and their reactive stabilities. In addition to chair and boat configuration discussed above, cyclohexane in the principle can adopt many other configurations. Of these only two twist boat and half chair configuration are important and well discussed now. The twist boat configuration has been obtained from the boat configuration as follow. Consider the model of boat configuration with the flagpole hydrogen pointed up and look down through the ring. If we hold the C1 C6 bond in a rigid hand and the C3 and C4 bond in the left hand and twist the molecule in such a way that C3 and C6 are go down and C1 and C4 are go up, we will find that the flagpole hydrogen move diagonally away from each other and the two hydrogen on the C3 and C6 being to be approach each other. If the motion is continued till the distance separate HA and HB become equal in two between HC and HD, a new boat configuration called twisted boat is obtained. In this configuration, the non-bonded interaction between the two flag hydrogen are at minimum, and also the torsional strain due to explicit interaction are on C1 and C6, C3 and C4 bond is particularly derived relative to the boat form. Consequently, the configuration of cyclohexane should be more stable than the boat configuration. And this prediction has been verified experimentally. The relative energy of the various configuration of the cyclohexane as shown in figure 3.39. From the potential energy diagram, it is clear that the chair configuration of the cyclohexane is more stable. It is about 2.97 mole stable than the boat configuration by the 23 mole more stable than the twisted boat configuration. In another word, the twisted boat configuration is only about 6.7 kilojoule more stable than the boat configuration. The two twisted boat configuration are mirror image on each other and hence are called elastomer configuration. These are separated by a small energy barrier of about 6.7 kilojoule per mole, at the top of which lie the boat configuration. Thus, the boat form of the cyclohexane is just transition state configuration, and the two anisomer twisted boat configuration can be get converted into each of by climbing this small energy barrier of 6.7 kilojoule mole. Unlikely the boat and the twisted boat configuration which are separated by a small energy barrier share configuration, and the twist boat configuration are separated by a large energy barrier of 46 kilojoule per mole. At the top of this energy barrier lie another transition state configuration called the half chair configuration of the cyclohexane. Since half this half chair configuration has considerable angle strain and torinal strain and steric strain, tucks the least stable at all the configuration of cyclohexane. Conformation of cyclohexane. Out of the four configurations, the cyclohexane discussed above two stable, more stable configuration. The chair and the twisted board configuration are called the conformer of cyclohexane, while the other two, boat and half chair, are only transition state configuration. The difference in energy between the configuration is just 23 kilojoule per mole, and this is small amount of energy and can be easily supplied by the coagulation of molecule at the room temperature. Hence, these two conformers are relatively interconvertible and hence cannot be separated at the same time. This energy barrier is large enough for each of these configurations to retain their identity. Further, due to the greater stability of chair form, on the average, one molecule is average 10,000 molecule exist in the twisted boat form while the other exist in chair form. In another word, for which all the practical purpose, cyclohexane almost exclusively exist in chair configuration. Axial and equatorial bond in cyclohexane. 12 hydrogen atoms of the cyclohexane can be divided into two sets, each containing the six, and those hydrogen atoms which lie above and below the general plane of the molecule are parallel to the axis of the cyclohexane ring are called the axial hydrogen atom, and the bond holding these hydrogen atoms are called the axial bond, and these are usually designed by the letter A. The other set of six hydrogen atoms which extend the radial outward at angle of 109 to each axis are essential situated among the equator of the cyclohexane ring are called the equatorial hydrogen atom and the bond holding them are called equatorial bond. These are generally identified by letter E. Configuration of monosubstituted cyclohexane derivative. The position of the axial and equatorial hydrogen on each carbon atom of cyclohexane ring are not fixed. In fact, these keep on interchanging. In another word, the chair conformation of cyclohexane is flexible at room temperature and one chair form is readily converted into another chair form. The process is called ring flipping and in doing so, the axial hydrogen in one chair conformation are converted into equatorial hydrogen in another word the another chair conformation and vice versa. Both these chair conformation are identical hence cannot be distributed. If, however, the hydrogen is replaced by the another group, the two forms are longer identical. Since all the mono-substitute cyclohexanes as monocycline can be exist into two conformational isomerism, one of having the methyl group in the axial position and other have the methyl group in equatorial position. Because of the steric hindrance between the bulk methyl group and non-bonded axial hydrogen on C3 and C5, axial methyl cyclohexane is thermodynamically less stable than the corresponding equatorial methyl hexane. Such type of non-bonded interconnected are called 1,3 diaxial interaction and tend to be destabilize the molecule. The extent of destabilization, however, depend upon the size of the substitute. For example, a methyl cyclohexane has two additional n-butane garage interaction than the corresponding e-methyl cyclohexane as shown below. Thus, it is clear from the above the projection formula that there is no n-butane garage interaction between the axial methyl and the C3 methylene group. Similarly, by drawing the n-butane projection about 1 3 1 C, carbon first and C carbon 6 bond, we can be sure that there is no more n-butane garage interaction between the axial methyl and does not have a such additional methyl garage interaction as shown below. So since here here is a E methyl and the carbon C and carbon C methyl are garaged anti-orientation. Stereochemistry of the axial of the equatorial configuration is also larger. For the example, in the case of tetrabutyl cyclohexane, the difference in the free energy of the two configuration is 22.6 kilojoule mole. Thus, the methyl is 5% of these molecules are in the chair configuration with an axial methyl group at the temperature. In the tetrabutyl hexane, on the other hand, only spot one molecule in 10 ki power 4 which have an axial tetrabutyl group, therefore can be said to be exist vertically exclusive in the configuration with the tetrabutyl group in the equatorial position. Conformation of the distinguished cyclohexane derivative. This substituted cyclohexane derivative have three positional isomerism: first, second, first, third, first, fourth. Each of these position isomers have the four geometrical isomers cis and trans. These Thus, in older disubstituted cyclohexane derivative, the six geometrical isomerism 1 2 cis 1 2 trans 1 3 cis 1 3 trans 1 4 cis 1 4 trans. We have already discussed that the most of the stable configuration of an mono-substitute cyclohexane derivative does substitute inversely occur the in crowded equatorial position irrespective of the size of the substitute. However, in the case of discontinued cyclohexane derivative depend upon the relative position and the geometry of the substituted meant both the substitutement may be either occur equatorially position but rarely axial position. One of the substitute may be occur axially and the other equatorial position as shown below. First, cis. Let us now discuss about the configuration of six geometrical one by one. First, cis 1 2 disubstitute cyclohexane. In this compound, one substitute always occur axial and the other equatorial position. For example, cis 1 2 ethyl dimethyl cyclohexane has one axial and one equatorial methyl group. Has one axial and one group. However, if the substitute are at different size, then avoid the destabilization by 1 3 diaxial interaction. The bigger the substitute occur, the uncrowded equatorial position. For example, in the case of cis 2 methyl cyclohexane, CH3 bond has been bigger in size than the OH group occur equatorial position. In general, greater the difference in the size between the two substitutes, greater will be the predominance of the configuration in which the bigger substitute occur equatorial position. Second, trans 1 2 disubstitute cyclohexane. In this compound, both the substitute occur either equatorial or axial position. Since each axial substitute has 2 1 3 diaxial interaction, therefore the diaxial trans 1 2 dimethyl cyclohexane is highly unstable. In another word, the trans 1 2 dimethyl cyclohexane predominantly exists in the diequatorial configuration. Further, this form will be more stable than the cis 1 2 dimethyl cyclohexane. Third, cis and trans 1 3 diethyl cyclohexane. In the case of cis 1 3 dimethyl cyclohexane, 2 methyl group can either be diequatorial or diaxial. Since diaxial form is destabilized by the 1 3 interaction and therefore cis EE form is more stable than the cis AA form. However, However, in trans 1,3-dimethyl cyclohexane, one CH3 group occurs equatorial position while the another occurs at axial position. The axial methyl suffer from 1,3-diaxial interaction. As a result, the trans 1,3-dicyclohexane is less stable than the cis 1,3-dimethyl cyclohexane. Thus, cis EE form will be the most stable configuration of the 1,3-dimethyl cyclohexane, and cis and trans 1,4-dimethyl cyclohexane. The cis isomer exist in two equivalent configuration while the trans isomer exists in two non-equivalent configuration due to absence of stabilization 1 by 1 3 diaxial interaction. The form of trans 1 4 dimethyl cyclohexane is more stable, followed by the cis 1 4 dimethyl cyclohexane AA form, while AA form of trans 1 4 dimethyl is least configuration. Stable configuration. Stability of 1 2 1 3 1 4 dicyclohexane. Out of the 6 geometrical isomers, the dicyclohexane 3 isomers cis 1,3 cis 1,4 and trans 1,4 dimethyl cyclohexane has been plain by the symmetry and hence are optically inactive achiral. In contrasting, the cis 1,2 trans 1,2 and trans 1,3 dicyclohexane has no element of symmetry and hence are chiral. Difference between configuration and conformation. The term conformation should not be confused with configuration, although both represent a conceptual arrangement of atom or group of atoms with a molecule, whereas the variance of the configuration of molecule can be easily interconvertible simply by rotating about a single bond. The different configuration of molecule can only be interconverted by breaking making the bond. In another word, the energy difference supplied by the collision of the molecule at room temperature. As a result, the conformation of molecules are rarely interconvertible and hence cannot be separate. For example, the segregated and explicit configuration of ethane cannot be separated. A configuration, on another hand, characterizes a particular stereoisomer of a compound. For example, in the cis-2-butene, the two methyl groups are on the same side of the double bond, while the trans-2-butene, the two methyl groups lie on the opposite side of the double bond. In another word, cis-2-butene represents a particular stereoisomer of 2-butene. Similarly, the trans-2-butene represents another stereo of 2-butene. Thus, cis-butene and trans-2-butene are conformantly isomer of 2-butene. As already discussed, because of hindrance rotation about the carbon-carbon double bond, the energy difference between is quite larger, and thus the large amount of energy cannot be supplied by the collision of the molecule at room temperature. As a result, the conformational isomerism cannot be really interconvertible. In another word, the conformational isomerism have independent and extended hence can be separated. Like the geometrical isomerism, optical isomerism are also conformational isomerism. For example, plus minus lactic acid and the S plus lactic acid can be interconvertible only by breaking and remarking the covalent bond, which required the 400 kilojoule of energy. Thus, optical isomers have independent exchange and hence can be isolated.